Chapter 1: Force, Work, Power and Energy. In this video, I will discuss work. Before this, I will give a small introduction about vector. A vector is a physical quantity having both magnitude, direction, and obeying the rules of vector algebra. In physics, we will come across large number of vectors. Example, displacement, velocity, force, etc. And the symbols we are using is for displacement we will use S, velocity V, force F, like this. A vector is denoted by writing arrowhead over the symbols representing it. For example, displacement is represented by the symbol S. To show that it is a vector, we will draw an arrowhead over it. Similarly, velocity vector will represent like this. Similarly, force vector will denote like this. Now, a vector is represented by drawing a straight line with an arrow mark. For example, vector F I will represent by a straight line OA like this. O is the initial point and this straight line OA with an arrow mark represents the force F. O is the initial point and A is the terminal point. The length of the straight line OA is proportional to the magnitude of the vector F, and direction of this force vector is given by the arrow mark, that is, it is directed from O to A. Now, modulus of a vector. Modulus of a vector means it is the magnitude of the vector. Only magnitude we are considering. The vector F will represent it like this, and the modulus of vector F we are representing by drawing two parallel lines like this, or simply we can write F. So now this is the vector F, and these two symbols will represent modulus of vector F. Now we will consider resolution of vector. Resolution of a vector. Resolution means it is the process of splitting one vector into two or more vectors. I will represent vector F by the straight line OC like this. And OX and OY represents coordinate axis. Now, the force F is making an angle theta with respect to x-axis. Now I want to split the vector F along OC into two vectors, one vector along OX and the other vector along OY. For this, I will drop a perpendicular from C on the x-axis. Now CA is the perpendicular and this OA represents component of vector F in the direction of x-axis. I will call this as Fx vector. Similarly, to find component along y direction, I will drop a perpendicular from C on y-axis. CB is the perpendicular and OB is the component of vector F in the direction of y-axis. I will represent this by Fy. Now from figure we can write like this: OC vector is equal to OA vector plus OB vector. This OC represents vector F, which is equal to OA represents Fx, vector Fx, plus OB represents this vector Fy. So vector F is splitted into two vectors, Fx along x direction and Fy vector along y direction. So these two vectors we are calling components of vector F. Now we can represent these component vectors by angle theta and the magnitude of vector F. In triangle OAC, we will consider cos theta, which is equal to adjacent side OA divided by hypotenuse OC. Or we can write like this: OA is equal to OC into cos theta. Now this OA represents modulus of vector Fx, that is equal to OC represents modulus of vector F. Therefore I will write F into cos theta. Similarly, in the same triangle we will consider sin theta, which is equal to opposite side AC divided by hypotenuse OC. Or we can write like this: AC is equal to OC into sin theta. Now this AC is exactly equal to OB. Therefore I will write here OB, which is equal to AC, that is equal to OC into sin theta. Now this OB represents modulus of vector Fy, which is equal to OC, it is modulus of vector F and sin theta. Okay, this is how we can represent one vector F into two vectors Fx and Fy. This process we are calling resolution of vector. Now we will consider work. It is denoted by the symbol W. In our daily life we come across the word work for various physical and mental activities like reading, writing, eating, etc. But in physics, work has a specific meaning. In physics, work is said to be done only when force is applied on a body and the body is displaced, that is, there is a displacement. Okay. For example, you consider a man pushing a car. Okay. Imagine this is the car. The man applies the force and the car is displaced from one position to another position. So there is force applied on the car and there is displacement. Then we say work is done by the person. Similarly, but if you consider the same man pushing a wall, consider he is pushing a wall, he is applying force on this wall, but the wall is not moving. That means there is no displacement. Displacement is zero. Force is applied by the man, but wall is not moving. Therefore, displacement is zero. Now work done is zero. Similarly, a watchman sitting in front of the school gate is also not doing any work according to physics because there is no displacement. But in ordinary language, we say watchman is doing work. Now, I will tell you how to measure the work. measurement of work. Work done by a force depends on two factors. One is force and the another one is displacement. Now, two cases we will consider. The force F, first one I will consider force F and displacement S are in the same direction. Consider a body placed at A at rest. Now we will apply a force F in this direction and the body is displaced from A to B in the same direction. Now this AB represents the displacement S and force is F. They are acting in the same direction, or in other words, the angle between them is theta, we will call 0 degree. Now in this case, work done is equal to the product of force and displacement in the direction of force. In the direction of force. Now we will consider expression for force. Here when force F and displacement S are inclined to one another, that is theta not equal, angle between them theta not equal to 0 degree. Here we can measure the work done by two methods. One is by finding component of displacement along force F, that is component of displacement in the direction of force. So here we will consider force F is applied on a body which is placed at A, and it is displaced in this direction from A to B. So AB represents the displacement and this is the direction of applied force. Let theta be the angle between the displacement and the force. Now we can find the component of displacement in the direction of force by drawing a perpendicular like this. Now BC is the perpendicular and this AC represents the component of displacement in the direction of force. That means we can measure like this: work done is equal to force into component of displacement along force direction. So W is equal to F is the force, for write F, into component of displacement in the direction of force is represented by AC. This is how we can measure work done. But in triangle ABC, in this triangle ABC, cos theta is equal to AC, this adjacent side, divided by hypotenuse AB, or we can write like this: AC is equal to AB into cos theta. Now this AB represents modulus of displacement, therefore I will write S into cos theta. AC is equal to S cos theta. This AC, which is equal to S cos theta, represents component of this displacement in the direction of force, that is along AC direction. Therefore now for this AC I will substitute here. So therefore work done W is equal to force into component of displacement in the direction of force is AC, which is equal to S into cos theta. This is how we can measure force. Okay. Similarly, I will explain how to measure the force or work done by finding the component of force. Second method, by finding component of force along displacement. Okay. Now consider a body which is placed at A, and imagine a force is applied in this direction. Force F is applied like this, and I will represent PA is the vector which is representing force. Now the body is displaced along AB. Now AB is the displacement which makes an angle theta with the direction of force direction. Now I want to find a component of force in the direction of displacement. For this, what I will do is I will drop a perpendicular from P on the displacement extended. Okay, so now this is the perpendicular. Pn represents the perpendicular, and this Na is called component of force in the direction of displacement. Now we can measure work like this. Work is equal to component of force along displacement into displacement. Now this component of force in the direction of displacement is Na, therefore I will write W is equal to Na into S. Now in this triangle, this triangle PNE, this angle is also equal to theta. These two angles are equal, and in this triangle PNA I will find out cos theta, so which is equal to Na adjacent side divided by hypotenuse P, or Na is equal to Pa into cos theta. Now I will substitute this Na in this equation. Therefore W is equal to Pa into cos theta into S. Now this Pa represents modulus of force F. Therefore W is equal to modulus of force Pa is F cos theta into S. So I will call it as equation 2. That is, work done is equal to the component of force in the direction of displacement, that is F cos theta, into displacement. Okay. Now we will consider special cases. case 1, when theta is equal to 0 degree. Here the force F and displacement S are in same direction. Then cos theta is equal to cos 0 degree, which is equal to 1. This is positive. Therefore W is equal to F into S into cos theta. If I substitute cos theta equal to 1, so we will get F into S into 1, which is equal to F into S. Here I will give one example. Consider a body at a height h above the ground. Imagine this is the ground. Body is at A, and this body of mass m is dropped from A, point A. Now this body falls freely towards the ground and reaches point B on the ground. Now height of the body h is actually displacement, which is from A to B, and the force acting on the body is the force of gravity F, which is equal to m into g, where m mass of this body and g is the acceleration due to gravity, or we will call this as weight of the body. Now we can observe the force F is acting in the direction AB, and displacement S is that is equal to AB, which is this is also in the same direction. Angle between them is 0 degree. Therefore work done W is equal to force into displacement, that is equal to force is mg, and displacement S, that is equal to h. Therefore work done is equal to mgh. Okay. In the second case, we will consider case 2. When theta equal to 90 degree. So here cos theta is equal to cos 90 degree is equal to 0. So in this case, the angle between force and displacement is 0. That is, force is acting in one direction and displacement is perpendicular to the force. Now theta 90 degree. So in this case, cos theta becomes 0. Therefore work done W is equal to F into S into cos theta. And if I substitute the cos theta equal to 0, we will get Fs into 0 is equal to 0. Therefore work done is 0 when the force and displacement are perpendicular to each other. Example, you consider a coolie carrying a luggage on his head. Okay, imagine he is carrying a luggage of load of mass m, and imagine he is walking in this direction, horizontal direction. Now the force acting on the coolie is to lift the body is in this direction F, which is equal to mg, and he is walking along horizontal. Therefore displacement is in this direction. That means force and displacement are perpendicular. Theta equal to 90 degree, and therefore according to physics, work done by this coolie is 0. But in ordinary language, we say coolie is doing work because he is carrying the luggage. But in physics, he is not, even though he is carrying luggage and walking horizontally, he is not doing any work according to physics. Now we will consider SI unit of work. The SI unit of work is joule, which is denoted by the symbol capital J, and we can define 1 joule. 1 J, which is equal to 1 Newton into 1 meter. That means work done is said to be 1 joule if a force of 1 Newton acting on a body and displaces it through 1 meter in the same direction. Similarly, we may use bigger units like kilojoule. So 1 kilojoule, which is written as 1 kj, that is equal to 10 to the power of 3 joule. That is 1 kilojoule is equal to 1000 joules. Similarly, 1 megajoule is equal to 1 mj, that is equal to 10 to the power of 6 joule. And also 1 gigajoule, which is equal to 1 gj, that is equal to 10 to the power of 9 joule. Okay. Now CGS unit of work. Erg is the CGS unit of work, and this 1 erg is equal to 1 dyne into 1 centimeter. Therefore, 1 erg is defined as the work done when a force of 1 dyne acts on a body and displaces it through 1 centimeter in the same direction. Now we can convert erg into joule. Okay. So we know that 1 dyne is equal to 10 to the power of 5 Newton, and we can 1 meter is equal to 10 to the power of 2 centimeter. So we know that 1 joule is equal to 1 Newton into 1 meter. Now we will substitute 1 meter is equal to 100 centimeter, and similarly 1 Newton, okay, 1 Newton is equal to 10 to the power of 5 dyne. Therefore I will write 10 power of 5 dyne here, 1 joule, or in other words 1 joule is equal to 10 to the power of 5 plus 2, we will write 7 dyne centimeter, we will call erg. That means 1 joule is equal to 10 to the power of 7 erg. This is how we can convert SI unit into CGS unit of work.